Hello, pre-calculus. Our objective for today is going to be to apply properties of vectors. I've got the checklist on the screen. You know what to do from here. Okay, I am going to force a pause on your screen, and I would like for you to try this warm-up for me. Let's see if we can get this a better window for you. There we go. So what I'd like for you to do first is find me the component form of a vector v whose initial point is 1, 3, and terminal point is 4, 7. And then go ahead and hit continue, see if that answer is correct, and then I'll go ahead and have you find the unit vector after that. So first just find me the component form. Okay, we're back. We should have gotten 3, 4 as our component form, and remember the component form is basically taking that black vector and moving it to the origin, okay? So if I start that vector at the origin, then it terminates at the point 3, 4. So that's my component form. Now do me a favor and find a unit vector. And remember, unit in math means 1, so I want a vector going in the same direction but with length 1. So try that and then hit continue when you want to check your answer. All right, we should have gotten 3/5, 4/5. Notice that the magnitude of the initial vector was 5, so if the original vector had a length of 5, we want to divide by 5 or multiply by 1/5 to shrink it down to have a length of 1. All right, I'm going to force a pause on your screen. Can you please copy what I have, and then we'll talk a bit more about the two forms of a vector. Okay, we are back. So the first form is what we've been looking at. It's component form when you have these angled brackets, right? Another form, which you may see more in like electrical engineering, is linear combination form. So this will be, instead of like v1 comma v2 in angled brackets, you'd have v1 times the vector I plus v2 times the vector j. Now the vector I is a unit vector of 1 comma 0, so it's your horizontal unit vector, and the vector j is your vertical unit vector. All right, so you may see, or you will see both, but just know how to convert between the two. All right, so kind of continuing on with that previous example, if we want to find a vector v with the given magnitude, which is 10, in the same direction as u, then what could we do? Now, keep in mind, this is in linear combination form, so this is also known in component form as 3, 4, which was that vector we were looking at earlier in the warm-up, okay? So we know that this given vector has magnitude of 5. We want it to have magnitude of 10, so what could we do? We could multiply everything by 2. So if I take 2 times the vector u, that would just give me 6, 8 in component form. Or, and just be really mindful, I do not care on the test which form you put it in, but my math lab obviously will care, so just be sure you read the little blueprint to know what form to put it in. All right, so we're going to look at the direction angle of a vector. I'm going to force a pause on your screen. Can you please copy what I have here, kind of just this graph, and let's go ahead and call this angle theta. So go ahead and copy what I have. Okay, we are back. So theta is the angle measured from the positive x-axis, so the initial side, to the vector, in other words, the terminal side, okay? So what I'm going to do is make our trusty right triangle here, right? And this is x and this is y. So now let's do this. Let's say that we've got this vector u. If this leg is x and the other leg is y, then would you agree that the hypotenuse is going to be the magnitude of the vector, right? So for the hypotenuse, I'm going to kind of slap on these magnitude symbols there. So that's going to give me the length of the hypotenuse. So if I want to find cosine of theta, let's write that, cosine of theta, that would be x over the hypotenuse, right, which is the magnitude of the vector, okay? And if I want to find sine of theta, similarly, that would be y over the magnitude of the vector, okay? Now, if I look at the first equation we have there and wanted to solve this for x, I would get that x is the magnitude of the vector u times cosine of theta. Okay, and similarly here, if I wanted to solve for y, I would multiply both sides by the magnitude of u. So y would be the magnitude of u times sine of theta. Okay, so let's write those here if you haven't already. So x is going to be this, and y is going to be this. Should look real familiar from unit circle, right? Sine is attached to y, cosine is attached to x. Okay, so if I want to write a u, you know, it was x comma y in component form, right? But now let's make that substitution. Well, x is the magnitude of u times cosine of theta, and y is the magnitude of u times sine of theta, right? And notice that they both have this magnitude of u as a factor. So what I'm going to do is I'm going to take that to the front and rewrite u like so. Okay. And this is called the trig form of the vector, all right? So make sure you've got that boxed. So here's our trig form of any vector. Now let's say that I wanted to get a vector into trig form. So we know how to find the magnitude. We know how to find this part of it, right? Now, how do we find theta? Well, do you agree that if we come back to our picture here, let's do this, that tangent of theta is y over x, right? So let's write that over here. Tangent of theta is y over x. So if I wanted to get theta by itself, I could cautiously take inverse tan of y over x, okay? And I say cautiously because especially if you are going to be calculating this on a calculator, your calculator is not going to know what quadrant you're in, okay? So I'm going to put a little asterisk here. Let's change my color. Little asterisk. And what I'm going to do is I'm going to put this inverse tan of y over x plus a being an angle, okay? So how do I know what to add? Because again, the calculator is not going to know what quadrant you're in. So it's if both x and y are positive, it's going to assume you're in quadrant 1, so you're not going to need to adjust for anything. However, if you are in quadrant 2, you're going to need to add 180 degrees. Same for quadrant 3. Now, if you have one positive, one negative, it's going to assume you're in quadrant 4. However, it's going to spit that angle out as a negative answer, if you remember that when we were doing arcs or inverse trig. So just add 360 to get the correct positive angle there, okay? So make sure you've got that kind of little guide in your notes so that you can adjust and make sure you get the correct angle, because again, your calculator is not going to know what quadrant you're in. All right, let's try an example together. I'm going to force a pause on your screen. Just go ahead and copy what I have and we'll work this together. We are back. So we want to find the magnitude and the direction angle theta for v is negative 12i plus 15j. Remember, this is just another way to say in component form negative 12 comma 15, right? All right, so for the magnitude of v, just good old Pythagorean theorem there, we're going to take the square root of negative 12 squared plus 15 squared. So 144 plus 225 inside the radical. This gives you square root of 369, which I believe is 3 square roots of 41. So that is the magnitude. Now to find the direction angle, so let's first come get a feel. This vector is going to be in what quadrant? So I've gone left 12, up 15. It's going to be in quadrant 2. Okay, so I'm looking for this angle. Okay, so I'm going to call that theta. So theta is going to be, if I do this in the calculator, inverse tan of y over x, right? But if I'm in quadrant 2, what do I need to add? I need to add 180 degrees. All right, let me pull up my calculator and we'll do that together. Ooh. All right, we do want to make sure we're in degree mode, so I can tell from right here that I'm in radian mode. So I'm going to go down here, hover over to degree, hit enter, and make sure that degree is highlighted. So now we're good, and if you go to your home screen again, you can tell what mode you're in right here at the top. It says degree. All right, so we are going to go inverse tan. So second, tan. I'm going to go alpha y equals enter to grab my fraction if you like. And then we're going to have 15 in the numerator. Remember y over x. Negative 12 in the denominator. And then I need to make sure I adjust for my quadrant. So plus 180. Now let's make sure we get an angle in quadrant 2. That is indeed an angle in quadrant 2, right? So I'm going to put 128.659 degrees if you truncate, and that is that. Now if I asked you to find the magnitude and direction angle of a vector in trig form, then it becomes really easy, right? Because remember, in trig form, that is the magnitude, and this is your angle, okay? So the magnitude in this case is 8, and theta is 135 degrees. All right, here's our last example. I'm going to force a pause on your screen. Make sure you at least write the numbers, and then we'll work this together. Okay, so a basketball is shot at a 59-degree angle with the horizontal direction and an initial speed of 7 meters per second. Find the component form of the initial velocity. This looks more intimidating than it is. All you have to do here to find the component form is convert or go back to trig form. So we're going to have that 7 is our magnitude. So I've got 7, and then we'll have cosine of 59 degrees, comma, sine of 59 degrees. Now let's go find 59 degrees, the cosine and sine of 59 degrees in the calculator. Okay, so I grabbed cosine of 59 degrees and sine of 59 degrees in the calculator and got 0.52 and 0.86 respectively. And then I just went ahead and basically distributed that 7, if you want to think of it like that. So multiply both by 7, and this is what you get. This is the component form of the initial velocity. So that's what they asked us to find. Now you will have one like this on MyMathLab. So just keep in mind, like, what did we just find? Well, the horizontal component is the horizontal speed of the basketball as it travels towards the basket, and the vertical component would be your varying vertical speed, okay? Varying because it's affected both by the initial speed and then that downward pull of gravity, okay? All right, you all, I will see you next time.